All right. So one of the key aspects of this reaction, key characteristics, is that we said it is stereo specific. Hopefully you saw that in the video. Stereo specific. Can somebody tell me what that means? Don't all speak out at once now. We want it to be like a mass, a mass problem. Can anybody who watched the video that got this part, can somebody tell me what that means? Stereo specific? No? All right. Well, I don't want a lot of dead space, so we're gonna keep moving. So what do you notice? So let's go back to this. This is my diene. This is my dienophile. Right? And so the dienophile, what's the stereochemistry on this double bond right here? Is it cis or trans? No,
Trans.
it's trans. Praise the Lord. Praise the Lord. This is a trans alkene. Is that right? And so when you do the 4+2, that trans stereochemistry has to be maintained. That's the point. That's what it means by being stereo specific. It means that the stereochemistry of your alkene, of your dienophile, is maintained. You have to excuse my little handwriting. It is maintained. So if you start with a trans alkene, then the groups on that alkene have to be trans in the product. All right. So if you look right here, you have a methyl group on this side, a CH3, and then you have this amide on that side. So let's put the arrows in. Let me erase all this stuff. I'll leave that. So we're going from, I'll erase that too. Right here to here, and then this pair of electrons is coming here, and then this pair of electrons is coming here. Right, and let's number it. 1, 2, 3, 4, and then 5 and 6. So in the product, this is going to look like, well, you know that the core structure is going to be a 6-member ring. So you can always just draw that in. And then this is 1, 2, 3, 4, and then 5 and 6. So between 2 and 3, that's where my new pi bond is going to be. Right, there's a bond between 1 and 6. You can see that here. And there's a bond between 4 and 5. All right, so what's on carbon 6, which is this carbon right here? What's attached to that?
Rest of that stuff with the oxygen and the methyl group.
The rest of that stuff? You're talking about the amide group right here?
Yeah.
Okay, all right. So I'm gonna put that here. But the key is that it can't be, they have to be trans because they were trans in the star material. So I'm gonna make this one go, put that on a dash. Right? Let me scroll over so I can write that nitrogen in. Right, so that's on a dash. And then the other piece on 5, that should be a methyl group. But since it's trans in the star material, right, it's got to be trans. They have to be trans in the product. Are you following that? So this, you see how this is dashed and that's wedged, right? That's what it means for the reaction to be stereo specific. It means that whatever groups are on that dienophile, if they're cis on the dienophile, they need to be cis in the product. And if they're trans on the dienophile, they need to be trans in the product. So let me get to a blank space and we'll do another one. Well,
Does it matter if you made the 5 dash instead
No,
of
no, either one can be dashed. It doesn't matter. That's a good question.
okay.
All right. So what about here? What would that product look like?
It's cis, so they'll both be on the same side.
Right. So this is a cis alkene, so we should get a 6-member ring. Is that right? Always, because it's a 4+2 cycloaddition. You have a double bond here, and then you can draw. I'll just make them both wedged. Right, but the groups have to be cis.
Could you have drawn them both dashed?
Yes.
Okay.
If they were cis, did you have to put the wedge or dash? Could you have just drawn a regular line or no?
No, if you just draw a regular line, that means that there's no stereochemistry indicated.
Okay.
Right. So you have to show it either being wedged or dashed so that the stereochemistry is known. Because if you know the stereochemistry over here, then you got to show it in the product.
Okay.
Yeah. Good question. All right. Any questions about that, about stereo specific? There's another.
Real quick.
Yeah. Let me scroll back up because I wrote it out right here. So it's just that the stereochemistry of the dienophile is maintained.
Okay.
Yeah. All right. So let's go to another example. Let me give you another example. And it's just to illustrate another concept about the reaction, right? So if we do this example right here, right? This is my diene, and then this is my. It's kind of sloppy. My dienophile. All right. One of the other key characteristics of the reaction is that the diene has to be what we call cis. Right. So let me illustrate that. So I can write my diene two different ways. I can write it like this, or I can write it like that. Right. This is what we call cis. And what all that means is that both alkenes on the same side of that sigma bond that's shown right here, right? That's holding them together. Right. And you can rotate around that bond. That you do have free rotation around that bond. And in theory, well, actually in reality, it will rather be S trans. That's why you have to have run the reaction at an increased temperature. So that's what that little delta sign is for over the arrow. It means that you have to increase the temperature way past something like 100 degrees for some of these reactions in order to have enough energy for your diene to adopt the S-cis conformation, because normally it would much rather be S-trans, which is this conformation over here. Right, but in order for it to react, it's got to be S-cis. All right, and so if I look at this example here, what's the first thing I need to do to the diene in order to make that reaction happen?
You have to make it
Make it cis.
Make it S-cis, because right now it's S-trans, isn't it?
Mm-hmm.
So in order for me to do that, I would write my diene. I'll put my double bonds in, and then each one of those double bonds has a methyl group. So one of those methyl groups will be. Let me erase that. I need more room. My diene would look like this, right? And then those two methyl groups will be like so. So then when I take that and react it with this, I should get a product, right? I'll put the arrows in here. here, and then here, I should get a 6-member ring, and the 2 methyl groups are here, double bond here, and then on this.
So did you just flip that other double bond down?
Yeah, I just turned. So what happened was, like, do you see? Let me zoom in here. Can you see that?
Yeah.
You see the sigma bond between these two?
Yes.
Like, I can rotate around that bond with no
Okay.
problem. And so that's the only way that I'm able to get the diene into the S-cis conformation is to rotate around that bond. So one of those double bonds is gonna have to flip.
Okay.
Yeah, good question. Man, let me erase that. Put my aldehyde in. All right, any questions about that? Now for this particular reaction, since the dienophile is not cis or trans, right? You're gonna you get 2 products. One of them where this bond right here is gonna be wedged, and the other one where it's dashed. All right, so you actually will get both products in this particular reaction. All right. Any questions about that? About the S-cis, S-trans?
Could you repeat that last statement you said one more time about
About the products?
Yes.
Yeah. So for this particular reaction, the fact that you have this group out here and no bias as to how the diene and dienophile can interact, you're actually going to end up with, I'll just draw the other product. So you're going to end up with one of these being, back to black, one product.